Hey everyone, this is the first video in the series of Calculus in Nutshell. In this video, we will learn about some very basic aspects of calculus. Let's begin. Calculus describes one of the most fundamental aspects of the physical world, how things change over time. To make use of it, we describe problems in terms of functions and their graphs. We'll begin by modeling a simple scenario, the area of a growing square. Now think what will happen as the side length of a square increases at 1 meter per second. Then its area grows at a constant rate, or it grows slower the bigger it gets, or it grows faster the bigger it gets. What you think? Yes. As we can see in the animation, its area grows faster the bigger it gets. But how much faster? Let's investigate. First, we'll write a function which models the area of the square. Suppose we have square, whose sides lengths are x. So its area will be x squared. Next, we will plot the points on the graph so their coordinates satisfy. Area for side length x equals x squared. On y-axis, we plot area of square, and on x-axis, we plot side length of square. Does the graph of the area of growing square is familiar to you? Yes, you get it right. It's a parabola. So now we've modeled the area of the square with a function and a graph. But can we use them to understand more about how fast the area of the square is growing? For that, we need to first understand what is slope and what is average rate of change. As we see in the previous animation, as time elapses, the area of the square increases as we increase its side length. Now we will use delta A to refer to the change in area and delta X to refer to the change in the side length. Let's see an example. Suppose the side length increases from 1 meter to 2 meter, then its delta A would be 3 meters square, right? On the graph, delta X and delta A are represented by moving horizontally and vertically from one point to another. The slope of the yellow line is given by delta A over delta X, which is equal to 3. Similarly, the slope of the line connecting the points on A of x at x equals 0 and x equals 1 is equal to 1. The slope of each line, that is delta A over delta x, is equal to the change in the area of the square when we increase the side length by 1 unit. As we can see, as x grows, the slope of A of x gets steeper. The slope of each line delta A over delta x represents the average rate of change of the area between each value. The line connecting two points on a curve is called a secant line. The slope of the secant line is equal to the average rate of change of the area between 2 points. We found the average rate of change between side lengths 0 and 1, and again between side lengths 1 and 2. But how fast is the area of the square growing in the instant when its side length is equal to 1? From the graph, we can see that growth rate of area at x equals 1 must lie between values 1 meter square per second to 3 meters square per second. To represent when x equals 1, we draw a line which touches the curve only at point 11 and has the exact slope of the curve at that point. This green line is called a tangent line. The slope of this tangent line equal to the instantaneous rate of change of the function represented by the curve at that point. To find the instantaneous rate of change at x equals 1, we need to find the slope of the tangent line at that point. But we cannot use our previous method to find the slope with a single point, because in that method the slope is computed by dividing the change in area by the change in side length between 2 points. With only 1 point, there is no change in area or side length, and we get 0 divided by 0, which is undefined. Since the slope of the tangent line is definitely some positive number, and 0 divided by 0 is undefined, this can't be correct. In order to find the slope of the tangent line and the instantaneous growth rate of the square, we'll need to develop a new technique for finding slope that we will discuss in next videos.